All right, welcome to this video on composites. Here we're going to study various composites, including particle reinforced, fiber reinforced, and structural components. We'll see that composites will consist of a combination of two or more individual materials that are used to obtain a property that's superior to the materials when they're on their own. The typical approach to understanding composites is to define one material as a matrix, tends to be the majority material in that sense, and the minority component will therefore be regarded as the dispersed reinforcement added to that matrix material. So again, the design goal here would be to obtain a more desirable combination of properties where we try to take advantage of the principle of combined action, and we'll show some quantification of that through a rule of mixtures approach in today's lesson. So, for example, we might be able to achieve high mechanical properties like strength while not compromising too much in the overall weight per unit volume or the density of the material. So be able to access materials that are low in density but high in strength. Okay, so composites are broken apart into three major categories, as we mentioned. Particle reinforced, so that would be the minority particle and a supporting matrix. Fiber reinforced, or structural composites, where things like laminates and sandwich panels can exist. In the first category of particle reinforcement, the two subcategories are distinguished by size of the particle, so there can be large particle reinforced composites, or we can have a more uniform small particle dispersion that is present, and that would strengthen the material that way. In fiber reinforcement, we can have continuous fibers. These would be generally on the order of inches in dimension, and these continuous fibers can be woven or aligned, okay? And the other category is where there's a discontinuous set of those fibers as a reinforcement. So these would be very short strand, chopped little fibers that are added to the matrix. In that category, there is approaches to align even short strand fibers within the matrix material, depending on processing approaches, or they can be more random in orientation. Okay. So some additional terminology. So we've already established that understanding what material is the matrix is important. So the matrix phase is the continuous phase around the dispersed phase. Okay. So what is the purpose of the matrix? Well, it is to transfer stress onto the dispersed phase. And also, the matrix may act to protect the dispersed phase from the environment should it be prone to oxidation or UV degradation, and so the matrix can play a role in that regard. Okay, so what type of composites exist based and classified based on their matrix? Well, we can have a metal matrix composite, or an MMC. We can have a ceramic matrix composite, or a CMC, or we can have a polymer matrix composite, or a PMC. And the complement component is, of course, going to be the dispersed or the reinforcement phase. And the purpose here, in the context of a metal matrix composite, the reinforcement would be responsible for increasing the yield strength of the material, increasing the tensile strength of the material, and providing resistance to deformation with time or creep. In a ceramic matrix composite, the reinforcement would be responsible for increasing the fracture toughness of the material, given that pure ceramics have very low fracture toughness. So here the reinforcement would be responsible for increasing that property. And in the polymer matrix composites, we're going to see that the dispersed phase or reinforcement would be responsible for increasing the stiffness or the modulus characteristic, increasing the yield strength, tensile strength, and also that creep resistance. So what type of reinforcements are known? Well, we mentioned particles earlier, fibers, and even structural approaches where laminates or sandwich type structures are constructed. Okay, so in ceramic matrix composites, we mentioned that if we were to look at the force versus displacement, something akin to stress versus strain, that an unreinforced ceramic would have very low fracture toughness and would not undergo very much plastic deformation, and so we would have a very sort of short data set represented by the purple line on the graph. However, when we introduce particles to reinforce that ceramic, that all of a sudden we can go to higher strength and ultimately get larger area under the force per displacement curve here, speaking to a toughened material. Okay, so fracture toughness would increase therefore. And in the case where fibers are included in that ceramic, you can see here that the fiber is especially impactful on increasing the overall toughness of the material, given the area underneath the teal curve here. And therefore, the fracture toughness would also be expected to increase as well. Okay, over in polymer matrix composites, some of the triumphs there are showcased best in a modulus versus density plot, where, as you might predict, the ideal territory to be in this space, given the dimensions on the graph, would be to be at very low density values for material, but to be high in stiffness. And that would be up in this near ideal territory here. Okay, so very low density, high stiffness materials are going to be excellent candidates for structural components in various applications like automotives, aerospace, or even nautical vessels. Ceramic materials, unfortunately, suffer in that they are higher density, but the proper stiffness. So the ceramics are not as good as alternative materials like PMCs, as we'll see. Metals and metal alloys do really well as well. They are high on the chart, but are often high density and often worse than ceramics. And pure polymers by themselves are kind of worse in both categories. So they're low stiffness materials and kind of modest density. And it's not until we combine polymer as a matrix material in a composite that we can achieve, the triumph material here that is as close as possible to the ideal territory on this modulus versus density graph. So the PMCs are some of the most competitive materials in this regard, and as close, if you want, to the ideal areas as possible. Okay, looking deeper at some options for particle reinforced composites. We've seen before in the cast iron series that we could afford cementite reinforcement or particles that would phase separate in the phase diagram that we learned in our previous lessons, and that these would act to prevent shear slip planes from that would otherwise lead to plastic deformation in the pure iron sample. So the alpha phase here would be the pure ferrite. It would be low carbon iron mix and would be the matrix. And the reinforcement would be the cementite, the iron carbide material that is brittle. Another example would be a situation for tungsten carbide and cobalt. And so here, in this case, the matrix is the cobalt material. It's very ductile and therefore tough. It gives us a lot of area under the stress strain curve. And the particles in this case would be tungsten carbide ceramic that would be brittle and hard, and again act to prevent plastic deformation by way of motion by way of shear planes in the metal matrix. And in a case from the automotive industry, rubber tires. Tire rubber is comprised of often a natural rubber that is very compliant and easily deformed. However, to make sure that there's sufficient stiffness to the material, often carbon particles or carbon black are added, as you see pointed in the diagram here.